Hello, and welcome to this Hellma Analytics presentation, where we are going to look at the projected return on investment for online analysis using process analytical technology in a chemical manufacturing environment. I'm Evan Friedman, Vice President of Hellma USA, and today we'll be looking at some of the cost savings and benefits that are possible through use of online process measurement in place of remote laboratory analysis. For every investment you make, however big or small, certain gains or benefits are always expected in return. Some of the benefits are tangible and quantifiable. Once we put a value on them, we can calculate a projected return on our investment. Along with these primary returns, there are intangible advantages that can't be quantified. They may be a spin-off from some of the tangible benefits like faster production runs, which measurably reduce manufacturing costs, but also enable shorter delivery times to your customers, giving the abstract benefit of improved customer service. Or your investment may help avoid waste and scrap, bringing the gains of reduced material costs and disposal charges. But that can also bring a more nebulous environmental benefit, and with it an improved relationship with your local community. Other seemingly unrelated intangible benefits may arise in areas like improved worksite safety, higher employee morale and motivation, or an enhanced brand image. So it's worthwhile to keep in mind that for every return on investment that you calculate, there are additional X factors that will likely improve the return further through systemic positive impact on your business unit. And although you can't put a fixed valuation on these soft gains, considering them alongside your projected financial return and payback timeline is worth it. Let's use the manufacturing of a polyurethane as an example to explore the benefits of online process analytical technology compared to traditional remote lab analysis. Polyurethanes are an elastomeric class of chemicals which are highly stressable, free of plasticizers, and widely used as insulating and structural materials. Polyurethanes are used in the building industry for insulating new buildings and renovating older ones. They're used in almost all refrigerators and freezers, whatever their size or purpose. They're used in the automotive industry for passenger comfort and safety, as well as noise and vibration reduction. They're used in furniture and fashion, especially high durability but comfortable footwear. While their insulating and filling properties are used extensively in industrial applications. They're a key ingredient in paints, varnish, resins, and surface covering liquids, as well as in adhesives and bonding materials. 4.5 million tons are produced annually in Europe, giving revenues of around 12.7 billion euros and directly employing 360,000 workers, with up to 4.7 million other jobs being supported indirectly. The reaction to make basic polyurethane could not be simpler. An alcohol or polyol is added to an isocyanate or diisocyanate. The resulting reaction produces polyurethane and heat. But of course, there are many variations on this theme driven by the final purpose, whether that be hard plastic, foam, liquid, or some other novel formulation. Chemical or metallic catalysts might be added to control the reaction rate. CO2 and water can be used for foam production, and quenching agents could be added to ensure that no unreacted cyanate or NCO groups are left in the finished product. So, now we're ready for some numbers. Let's take a look at the most simplified example so we can model costs at the microscale. We see that the inputs of the raw materials give us a cost of 3 euros to produce 2 kilos of end product. We can sell those 2 kilos for 2.5 euros each. With distributed costs of 1.5 euros each, we make 2 euros profit on that 2 kilograms, or 1 euro per kilo in general. Maybe that doesn't seem worth doing. That is until you multiply it out by annual production. For a plant making 7,000 metric tons per year, gross profit results in 7 million euros. In order to properly understand the value proposition of online analysis in polyurethane manufacturing, we first need to understand the costs and limitations of quality monitoring by traditional laboratory analysis. I'm going to use some very conservative numbers here just to show how quickly the costs add up. Our example site has 4 reactors maintaining continuous production. Let's say quality control samples are taken to the lab from each reactor every 8 hours, so 3 times a day. This in and of itself demonstrates a critical limitation. The extracted sample is no longer under the same conditions as the bulk material remaining in the reactor. If the lab is running smoothly, it will probably take 1 or 2 hours to get results back to the production managers, by which time the reaction has progressed and the lab results, when available, are not truly representative of the current status. Once we estimate a rough cost of €50 per sample, which includes reagents and consumables for all analytes of interest in each sample, our equation can be solved, indicating the total cost for lab analysis could be up to €219,000 a year. If we modify these numbers just a little to reflect a facility that only operates 220 days, but samples every 2 hours, so 12 times a day, we see that the cost for lab-based quality control quickly balloons to €528,000 a year. A high cost for results that reflect what has happened rather than what is happening right now. Because of this time delay, inappropriate interventions or condition changes may be made, resulting in poor yields, reduced quality, or complete batch failure. This in turn has multiple impacts: lost raw materials, lost profit margin, waste disposal costs that we won't even include in our estimates, and maybe most importantly, wasted time. You can see from our example, this has the potential to add up to at least €60,000 for just 2 batch failures. One of the main advantages of online analysis is its real-time monitoring of the reaction. And whether you link that to automatic or manual control, this enables immediate intervention if something starts to drift off target, ensuring much closer control right up to the endpoint of the reaction, with little dependence on the individual operator's judgment and experience. This in turn will save time and material while increasing yields. We've given just a 3% improvement in our example, but much more should be possible in many circumstances. Here, that 3% time savings equates to something like an additional €210,000 a year in profit on additional product made and sold. To be clear, switching to online analysis will generate some savings on lab expenses, but for our example case, we're going to assume some laboratory work will continue. So let's put that at €180,000 savings instead of €219,000. Then there will be the savings from not spending on waste and disposal, and the positive improvements in production. Altogether, that comes out to a return of around €450,000 per year once the initial costs are recouped. So, what do those initial costs actually look like? Like all shopping lists, it can be more or less depending where you buy from and what options you select. An important savings in this list is that we are leveraging a single spectrometer system and a multiplexer that will switch between the different probes as each reactor is tested, saving the cost of 3 additional spectrometers. The cost of the fiber optic cables and their installation will vary depending on the layout of the specific plant. A control room near the reactors can help save some costs there. Similarly, with the process control system, if an easy interface to an existing system is possible, savings can be had here too. Finally, during commissioning, a calibration model will have to be created. This is done by referencing against the existing laboratory testing of standards and unknown samples. The calibration model will need periodic maintenance, which is one reason that the laboratory costs do not drop completely to zero. For this example, the investment into PAT is about €250,000. Now that we have all of these factors, the return on investment and payback term are very simple calculations. From the work we've done, we can consider that the net profit will increase by the total of the cost savings identified, €450,000, and that the investment needed would be €250,000, giving a very credible 80% return on investment. Similarly, the payback term is just 6.7 months. With the investment recovered within the first year, the savings then go on to accumulate year after year after year, with just minimal residual costs for maintenance and calibration of the online system. Real-time information lets you know what is going on when it happens, thereby helping you set and adjust the reaction conditions to optimize production. With everything optimized, production times should be reduced, enabling more product to be manufactured in a given amount of time. With a robust and tested calibration model, the same high-quality product will be produced batch after batch, without rejects, waste, or disposal costs. No longer will someone have to take samples from the reaction vessel and transport them to the laboratory. Now reactor conditions will be apparent in the control room, and potentially, actions can even be taken remotely. There is reduced need for bodies on the production floor, so employee health and safety will improve too. And of course, as I've shown here with a payback term of less than 7 months, there are considerable cost savings to be had year after year. And of course, there are those smiling faces, motivated employees, and satisfied customers who will be adding to your business in many other ways too.